For this video, we're going to be focusing on symmetry when it comes to these geometric shapes. The first type of symmetry that we're going to talk about is reflectional symmetry. Reflectional symmetry is when a reflection maps a figure onto itself. The line of reflection is called the line of symmetry. The best way to think about this is, where can you draw a line on a shape and perfectly cut it in half so that both sides are the same? Think about like a butterfly and a butterfly flapping its wings. It's perfectly symmetrical on both sides. So if we look at this rectangle, the first place that we could possibly cut it is going straight up and down vertically. If we do that, it creates two halves of the rectangle that are perfectly congruent to each other. The next way we could cut it is going left to right, horizontal. That also creates perfectly congruent halves of the shape. But those are the only two places that you could cut it. If you went diagonal with this rectangle, this corner would not be matching up with anything. This corner would not be matching up with anything. Only going horizontal and only going vertical allows you to be able to perfectly cut this rectangle symmetrically along those lines. The next type of symmetry that we could talk about is rotational symmetry. And rotational symmetry is when an image is mapped onto the pre-image after a rotation of less than 360 degrees. What that really means is being able to rotate an image, and then when you're done rotating it less than 360, so you haven't gone a full circle, when you're done rotating it, it almost looks like you haven't done anything at all. So if we look at this triangle, if we focus on just the top part of this triangle right here, make that your frame of reference. If I rotate this triangle just a little bit, it almost looks like I haven't even moved it. But I know I have because the red tip is down here in the corner. It started up top, now it's in the corner, but the triangle itself almost looks completely the same. And then if you rotate it again, it's now in the other corner, but still the triangle looks unchanged. And then we do our last rotation, it's back to its original spot. So each of those three movements, the triangle looks like it hasn't moved at all, but I'm actually rotating it. That's rotational symmetry, being able to rotate the shape, but it looks like you haven't even moved it. Whereas if we look at this trapezoid over here, this trapezoid, I have to go a full 360 to be able to get the same shape again. So the trapezoid has no rotational symmetry because the only way to see it back to its original spot is to go all the way around. And so that's an example of something that has rotational symmetry and something that does not have rotational symmetry. And the last type we can talk about is point symmetry. Point symmetry is just a subset of rotational symmetry. But point symmetry is when an object is rotated 180 degrees and the pre-image is equal to the image. So if we look at this double-sided arrow, if we just go a little bit, like 90 degrees, it's not going to match up. You have to take this shape and rotate it the full 180 degrees to be able to map it back up onto itself. And then it's a full 180 degrees for it to go back. So because it has that 180 degree rotation to it, that makes it specifically point symmetry. So it's still rotational symmetry, but it's very specific because it has just the 180 degrees. So if we look at these two shapes, we want to determine how many lines of symmetry each of these shapes has. Now, if you're not a visual enough person to be able to just look at a shape and kind of come up with where those lines are at, you can get something like patty paper and be able to trace the shape and then just fold the patty paper up and see which ways end up working. For the rectangle, we've already seen it for the definitions. We could slice it vertically up and down, and we could slice it horizontally left and right. And then for the trapezoid, there's only one place that we could cut it, and that is going straight up and down vertically. That would map up everything onto itself. The next one says, what are the rotational symmetries for the figures that are shown, and do they have point symmetry? So if we look at this star, we're able to rotate that star 4 times around before we go back. And each time that we rotate it, we get the exact same shape, almost as if we haven't rotated it at all. So the star has point symmetry, or has a rotational symmetry, and specifically we can spin it 4 times. If we look at the oval, we have to go an entire 180 degrees to be able to get the same shape showing up. And because it's 180 degrees that we're rotating, the oval is what we would call point symmetry. Looking at these two figures, we want to determine what types of symmetry, if they have any at all, what types of symmetry do they have, and then if they have a certain type of symmetry, how much of it is there. So if we look at this flower, we want to say, okay, is there any line symmetry, reflectional symmetry? Can I draw a line anywhere through here and be able to fold the flower up on itself? Well, the first line that I see is that I could go straight down the middle, and if I do that, everything on the flower is matching up with something on the other side. It's perfectly being mirrored. I could go down the other petal, and again, all of the parts of the flower are matching up with another part on the other side. Go through the next petal, it's the same thing, the next petal, and I'm seeing that I have 5 lines of reflectional symmetry that I could draw through this flower. So long as when you draw a line, you have parts that are perfectly mapping up with another part on the other side, that's reflectional symmetry. So what about rotational? Well, if I look at this shape, I could rotate it from this blue part to the next blue part, and the entire flower would map up onto itself. And I can do that a total of 5 times. So the rotational symmetry here is there, and I can spin this shape 5 times and be able to come up with the same shape again. So the flower has both rotational and reflectional symmetry. As I look at this little playing card kind of figure over here, there is nowhere that I could draw a line going through it because these 2 dots are kind of messing up the image. If I go straight down, this dot's not mapping up with any other dot. If I go straight across, these dots aren't mapping up with anything. And if I go diagonally, well, the corners aren't mapping up with anything. So there is no line symmetry for this figure. But I could rotate this shape 180 degrees and I would get the same shape again. So there is rotational symmetry. I can spin this shape twice. And that takes us into this next question. We want to look at which of these 2 shapes has rotational symmetry. So we have A, B, C, and D. 2 of them have rotational symmetry. Well, if we look at C, anywhere you rotate it, this little point is going to be pointing in opposite directions, so C is out. If we look at D, we've already talked about trapezoids, which means by default, A and B are the only 2 that are left. So A, if you rotate it 180, you get the same shape back. And B, if you rotate it also 180, you get the same shape back. So A and B are the 2 shapes that have rotational symmetry. Now, C and D still do have symmetry though. C has reflectional symmetry. If you draw it straight through these 2 points here, you can fold it up. And then D, going vertical with it, has reflectional symmetry as well. So they don't just not have anything, they just don't have rotational symmetry is all. So next we want to look at finding the order of rotational symmetry, the ORS. That is the number of times a shape can be rotated and still be the preimage. So we saw this with the flower and the playing card. The flower had 5 times that you could spin it. That 5 would be its order of rotational symmetry. Once you find the order of rotational symmetry, you can use that to find the angle of rotational symmetry. You do that by finding the ORS and then doing 360 divided by it. So if we look at these 2 examples here, our recycling symbol, we can rotate this shape 3 times before we're back to the original shape. So that means our ORS is 3, which means our angle of rotational symmetry is 360 divided by 3, which is 100 degrees. So every single time I make a rotation, I'm rotating this shape 120 degrees. If we look at the star, similar story. The star, I can rotate it 5 times around before I'm back to the original image. So our ORS is 5, which means our angle of rotational symmetry, 360 over 5, is 72. So each of these turns that I took was 72 degrees. So looking at these shapes, we're going to figure out what is the ORS and the angle of rotational symmetry. So this shape, I could rotate it once, twice, 3, 4, 5, 6 times to go all the way back around. So the ORS here is 6, meaning that the angle of rotational symmetry is 360 over 6, which is 60 degrees. Then looking at the next one, we could go once, twice, 3 times, 4 times, 5 times, 6 times, then 7 times before we're back at the original shape. So the ORS here is 7, giving us 360 divided by 7, so about 51.4 degrees is what we're dealing with this shape. So given these 5 shapes, we want to see if there's any reflectional line symmetry for any of them. And again, this is very visual, so if you have a hard time looking at a shape and coming up with it, this is where getting something like patty paper, where you can trace the shape and kind of fold it up and see if it's matching, will help out greatly. So for our first shape, we could draw it up and down. That gives us 1. We could go left and right. That would give us 2. These would map up. Those would map up. Those would map up. We could go diagonally through it, matching everything together, going diagonally again through the points, and then going through the other direction. So these 2 diagonals followed by those. So this one has 6 total lines that any of those lines you drew on it would perfectly cut the shape in half symmetrically. Going over to the butterfly looking shape, we could go once down the middle, once across the side, and then once through each of the petals, and that would perfectly mirror the shape onto itself. So this one has 4 in total. If we go down to our square, we can't go straight down because this little half circle is stunting it off. We can't go across because of that circle as well. We can't go down this diagonal because again there's nothing to match it up with. So the only place that we could draw a line to make it symmetrical is the downward slope diagonal here. That would map everything perfectly across to the other side. So this one only has 1 line of symmetry. Then if we look over here at the star, it is kind of the exact same shape as the first one. So that means that we're going to be able to draw basically the same amount of lines as that first one. So we get 6 lines being able to cut this shape up. And now lastly, the middle. If this circle was connected all the way through, we would be able to say that there's a bunch of lines that we could draw. But because this circle is gapped right here, any line that we draw going across it, this shape is being messed up because this is only symmetrical going down, but the circle is only symmetrical going across. And so because of that, this shape has 0 lines of symmetry for it. So what if then we looked at the ORS and the angle of rotation? So our first shape, again, if we highlight part of it so we can watch it rotate, we've got 1, 2, 3, 4, 5, 6 times we can rotate it and still come up with the same shape, meaning 360 divided by 6, our angle is 60 degrees here for every rotation. If we look at our next one, the one in the center, we have to go all the way around to get the same shape again. So this one has 1 order of rotational symmetry because you have to go all the way around, meaning that the angle is 360. So it does not have rotational symmetry, but there is still an order. The order is just 1. 1 rotation all the way around gets me back. Looking at the butterfly shape, we can go once, twice, 3 times, 4 times before we're back. 360 divided by 4 gives us 90 degrees. Looking at the square, we have to go all the way around to be able to get a shape that is similar to the original. So this one is 1, so the angle is 360. And then lastly, looking at the star, we can go once, twice, 3 times, 4 times, 5 times, and 6 times around, giving us 60 degrees as our angle. So to end this, looking at symmetries, we have these several shapes in front of us. I would say take a moment, pause it, see if you can get the correct answer for the ORS, the angle of symmetry, and a number of lines of symmetry. And then I'll go through the answers kind of quickly. So for the first one, we have an order of rotational symmetry of 4, so we can rotate it 4 times around. This makes my angle 90 degrees, and then our line symmetry is 4, going up and down, going left and right, and then through the diagonals. Number 2, we have an order of rotational symmetry of 6, so you can rotate it 6 times around. This gives me an angle of 60 degrees, and we have 0 line symmetry, nothing that you can actually draw through this. Number 3, we have an order of rotational symmetry of 2, so 180 and 180 back. Angle would be 180 degrees because of that, and then line symmetry 2, up and down, left and right. Looking at 4, we can spin it 3 times. This gives us degrees of 120, but there is no line symmetry here, nowhere I could draw a line going through it. Number 5, we can rotate it 4 times around. This means that it's 90 degrees, but there is 4 lines of symmetry, up and down, left and right, and through the diagonals. For number 7, order of rotational symmetry is 3. You can spin it 3 times around. The angle is 120. And again, there is no lines of symmetry that you could draw through this. And lastly, number 9 is very similar to number 2. Order of rotational symmetry is 5. The AOS is 72 because of that. And there is no lines of symmetry. And so the last thing we want to talk about when it comes to symmetry goes back to the idea of transformations and rotations. What angle would map A onto B? How would I go from A to B? Well, this shape has 6 spins to it. The ORS is 6, so 360 divided by 6 is 60 degrees. So if I do that twice, 120 degrees would take me from A to B. And if I expand that, if I look here, rotation has to be positive. That is counterclockwise movement. So the only way to get from A to B is to rotate 5 times around, giving me 300 degrees.